Greetings! In today's lecture, I'll present the Elliptic Curve Diffie-Hellman Key Agreement Scheme, ECDH. We'll see the importance of authenticating exchange points in order to prevent against malicious intruder-in-the-middle attacks. Elliptic Curve Diffie-Hellman Key Agreement, ECDH, is the elliptic curve analog of the Key Agreement Protocol first proposed by Diffie and Hellman in 1975. Recall that Diffie and Hellman, together with Merkle, invented the notion of public key cryptography in the mid-1970s. Diffie and Hellman were the first to propose the notion of a digital signature scheme, and they proposed the first practical key agreement scheme. For their work, Diffie and Hellman were awarded the Turing Award in 2015. The objective of ECDH is for two communicating parties, Alice and Bob, to agree upon a shared secret key K. Alice and Bob can then use the key K in a symmetric key scheme such as HMAC for authentication or AES-GCM for authenticated encryption. ECDH has some domain parameters. These parameters are fixed, public, and used by all entities in an application. The domain parameters consist of an elliptic curve E defined over the integers modulo p. For example, the curve P256. The number n of points on the curve, which is a prime number, a generator point P, which can be any point on the curve except the point at infinity, and a key derivation function KDF. Here is the basic version of ECDH called Unauthenticated ECDH. Alice begins by selecting a random integer x between 1 and n-1. She computes the point X by multiplying integer x and point p, and sends the point X to Bob over the unsecure channel. Note that x is Alice's secret because computing x from X is precisely an instance of the ECDLP, which we're assuming to be intractable. Bob then selects a random integer y between 1 and n-1, computes the point Y by multiplying y and p, and sends Y to Alice over the unsecure channel. Bob multiplies the point X he received from Alice by his secret y to get the point K. He applies the KDF to the point K to get a bit string k. Alice multiplies the point Y she received from Bob by her secret x to get the point K, and then she applies the KDF to K to get the bit string k. K is a secret key that is shared by Alice and Bob. I'll note that Alice and Bob indeed compute the same key k. This is because the shared secret point that Alice computes is x times y, where y is y times p. I can write this expression as x times y all times p, and then of course x and y commute, and so I can rearrange this expression as y times x all times p, which equals y times X, which is the point that Bob computes. So Alice and Bob compute the same point K, and thus the same key k. An eavesdropper who sees the points x and y, and also knows the domain parameters, which are public to everyone, is faced with the task of computing the shared secret point K. This is known as the ECDH problem. The fastest known attack to solve this problem is to first compute x from X, or y from Y, which are instances of the ECDLP. Thus, assuming that the ECDLP is intractable, the ECDH problem is also intractable. Hence, a passive adversary who sees x and y is unable to compute the shared secret key k.
Let's do an example of ECDH using the P256 elliptic curve. This example will give you a sense for the size of the numbers that are used in practice. Here's the prime P. Here are the coefficients a and b of the elliptic curve. Here is the number n of points on the curve. And here is the chosen generator point P. I'll define xp and yp to be the x and y coordinates of P. We'll first check that xp and yp satisfy the equation of the elliptic curve. And also check that n times p is the point at infinity. The Maple routine random generates a random integer in the interval between 1 and n-1. So in ECDH, Alice generates a random number little x, computes the point capital X equals little x times p, and sends the point x to Bob. Similarly, Bob generates a random number little y, computes the point y equals little y times p, and sends the point capital Y to Alice. Alice computes k1 by multiplying her secret integer x and the point y she received from Bob. Similarly, Bob computes k2 by multiplying his secret integer y and the point x he received from Alice. And, as expected, k1 equals k2. Alice and Bob then derived the shared secret key little k from k1 and k2, using a key derivation function.
This basic version of ECDH is unauthenticated because the points x and y that Alice and Bob exchange are not authenticated. So when Alice receives y from Bob, she doesn't have the assurance that y was indeed sent by Bob. Y could have been sent by an entity impersonating Bob. Since x and y are unauthenticated, unauthenticated ECDH is vulnerable to a malicious intruder-in-the-middle attack, MITM. This attack is more commonly called a man-in-the-middle attack, but I prefer the more descriptive term malicious intruder-in-the-middle attack. Here is the MITM attack on unauthenticated ECDH. Alice sends her point x to Bob. Eve intercepts this point and replaces it with the point x primed of her choice and sends x primed to Bob. Here, little x primed is a secret that Eve selected. Bob assumes that x primed was sent by Alice. He then sends y to Alice. Eve intercepts y, replaces y by y primed, and sends y primed to Alice. Bob now computes y times x primed to get the point k2, and then computes the secret key k2 by applying the key derivation function to capital K2. Similarly, Alice computes the point capital K1 by multiplying little x and y primed, and computes k1 by applying the KDF to the point capital K1. Alice thinks that K1 is a secret key that is shared with Bob, whereas Bob thinks that K2 is a secret key shared with Alice. However, Alice does not know K2, and Bob doesn't know K1. Moreover, the adversary can compute both K1 and K2. Suppose now that Alice encrypts the message M using K1 and sends the resulting ciphertext C to Bob. Here, E might be a symmetric key authenticated encryption scheme such as AES-GCM. The eavesdropper Eve intercepts C, decrypts C using K1 to get the plaintext little m, and re-encrypts M using the key K2 to get the ciphertext C primed. Eve then sends C primed over to Bob, who decrypts C primed using K2 to get the plaintext M that Alice sent. But Eve has also obtained M, and so Eve has compromised the confidentiality of Alice's transmissions. I hope you appreciate that the malicious intruder-in-the-middle attack is a real threat in practice. In fact, these kinds of attacks are possible in a wide variety of protocols if exchanged quantities are not properly authenticated. To circumvent the attack, the exchanged points x and y need to be authenticated. This can be done in a variety of ways. Here's a basic version of authenticated ECDH. Alice sends Bob her point x and her ECDSA signature on x. She also sends a certificate for her ECDSA public key. A certificate is an electronic document that asserts that a public key belongs to Alice. This document would have been signed by a trusted certifying authority, and Bob can verify the authenticity of this document using the certifying authority's public key. So Bob verifies the certificate using the certifying authority's public key, and then uses Alice's public key to verify the signature on X. If the signature is valid, then Bob has the assurance that Alice did indeed send X. Similarly, Bob would sign Y, and Alice would check the signature to confirm that Y was indeed sent by Bob. Authenticated ECDH prevents malicious intruder-in-the-middle attacks because when Eve replaces Bob's Y with its own Y primed, Eve is unable to compute Bob's valid signature on Y primed. This is assuming that the signature scheme employed is secure. Hence, Alice will reject Y primed and the attack will fail.
There are many subtle security issues that arise with authenticated ECDH, and, more generally, with key establishment. A good resource that offers a comprehensive treatment of authentication and key establishment protocols is the book by Boyd, Mathuria, and Stabila.
Google was the first large company to begin using elliptic curve cryptography in large-scale applications on the Internet. In November of 2011, Google started using ECDH instead of RSA as its default key establishment mechanism in TLS-secured applications, including Gmail and Search. ECDH was chosen because it provides forward secrecy, which I'll explain next. I'll describe forward secrecy in the context of TLS. When a client, who I'm calling Alice, visits a secured web page, who I'm calling Bob, Bob first sends his certificate to Alice. His certificate contains Bob's identifying information and his RSA public key. Alice verifies the signature in the certificate using the CA's RSA public key, which is embedded in her browser. If the signature verifies, then Alice is assured that she has an authentic copy of Bob's RSA public key. Alice then selects a random session key K and encrypts K with Bob's RSA public key. Alice sends the resulting ciphertext C to Bob. Bob decrypts C using his RSA private key and recovers K. And so K is a secret key shared by Alice and Bob. The session key K is then used to authenticate with HMAC and encrypt with AES, all data exchanged for the remainder of the session. TLS, as I just described, does not provide forward secrecy, by which I mean the following. Suppose that an eavesdropper, this could be the NSA or some branch of law enforcement, captures the ciphertext C, and also the encrypted data that was encrypted with the session key K. Suppose that at a future point in time, the eavesdropper wishes to decrypt the encrypted data. For that, she will need the session key K, and so she needs to decrypt C. If the eavesdropper is able to break into Bob's machine and learn his RSA private key, then the eavesdropper is able to decrypt C and thus recover K, and subsequently the data that was encrypted with K. Another option, instead of breaking into Bob's machine, is for law enforcement to demand that Bob hand over his RSA private key. Perhaps law enforcement also has a court order from a judge. In this way, law enforcement might be able to decrypt the encrypted data a long time after Alice sent the data to Bob. In this sense, TLS does not provide forward secrecy. ECDH can be used instead of RSA encryption to establish the session key in a way that provides forward secrecy. This is how Google incorporated ECDH into TLS in November of 2011. When a browser, Alice, connects to a secured website, Bob sends his certificate to Alice. Alice verifies the signature in the certificate using the CA's RSA public key. If the certificate verifies, then Alice is assured that she has an authentic copy of Bob's RSA public key. Alice then selects a random integer x, computes the point X equals x times p, and sends X to Bob. Here, p is a fixed point on the P256 elliptic curve. Bob selects an integer y, computes the point Y equals yp, and signs y with its RSA signing key. Bob sends the point y and its signature to Alice. Alice verifies the signature using Bob's RSA public key, and thus is assured that y was indeed sent by Bob. Alice and Bob both compute the shared secret point K, and then derive the session key k from K. Next, Alice deletes her secret x, and Bob deletes his secret y. The session key K is used to authenticate and encrypt, perhaps with AES-GCM, all data exchanged for the remainder of the session. At the end of the session, Alice and Bob delete the session key K. Note that forward secrecy is provided. If an eavesdropper, such as law enforcement, has captured the ciphertext and wishes to decrypt it, law enforcement needs the session key k. However, both Alice and Bob have deleted the session key K and all the secret keying material needed to compute it. In other words, x and y. Thus, even though law enforcement might present either Alice or Bob with the suitable court order for providing x, y, or the session key K, Alice and Bob are unable to respond to the court order because they have long deleted X, Y, and K. And so law enforcement is unable to recover the session key and decrypt the data that Alice sent to Bob. In this example, I'm assuming that both Alice and Bob have long deleted the plaintexts from their machines. Google values forward secrecy because they need to provide the assurance to their customers around the world that their data will be kept confidential, even when Google is presented with the appropriate court order to give the data to law enforcement. You can read more about Google's rationale for using ECDH for forward secrecy in this blog article. Let me conclude by describing the ECDH stack. In other words, the different layers of mathematical routines needed for a complete ECDH solution. At the lowest layer, one needs a library for multi-precision integer arithmetic, including addition, subtraction, and multiplication. Next, one needs a library for modular arithmetic, so addition, subtraction, multiplication, and inversion modulo prime p. One can then implement the elliptic curve addition law, which includes negation, addition, and doubling. Next, one implements elliptic curve point multiplication, the most important operation in ECDH. Now one can implement the ECDH protocol itself. Finally, one needs a public key infrastructure for exchanging authenticated public keys that are used to verify signatures on the ECDH points X and Y.
Video lecture V8d will conclude our study of elliptic curve cryptography. We'll describe the elliptic curve digital signature algorithm, ECDSA, and compare it with the RSA signature scheme. Take care!